we've started to talk about suffix arrays last time already. But before we continue with that, I want to do a small recap question. Because we covered a lot of complicated and intricate concepts last time. And before we rush on with the construction of suffix arrays, which will essentially be the topic for today, I want to make sure you remember the details of that. So let me now head over and start that question. This is all just a repetition of definitions that we covered last time. Okay, my laptop is a bit busy with this. Let me do it on the phone then. So I'll try to start the question for, say, 3 minutes because it's a really long one. If I only manage to click on it. Okay, now I started it with 1 minute, but maybe you had enough time to read it. Okay, I'm fighting a little bit with the tech here. Whenever I change windows, it's fairly slow. Okay, I hope you had enough time to vote on this. A bunch of people managed to vote. Maybe not everyone is here anyways today. I'll leave some more time for the next question. Let's briefly look at this. I'll try to squeeze it all on one screen. All right, so the question was checking all the correct statements, and I want to highlight the correct answers. And okay, come on, move back. So number A was we require the text to end with this end of word marker. Well, that's how we always did it, and for all the constructions that we use, that's necessary, so that's correct. The size of the suffix tree can be quadratic in the worst case. Fortunately, that is not true. That was true for the standard trie, but because C is not correct, the suffix tree is not a standard trie, but a compact trie. That's the only difference between C and D, which you could see more nicely here, but it's a bit hard to see in the text. So because the suffix tree is a compact trie, its size will always be linear in the number of strings that it stores, and that happens to be n, the number of suffixes, or roughly n. So this number B is not true, but number D is true. That's the definition of the suffix tree. Except E, that was again something that's not true. The leaves in the suffix tree don't have to store a copy of the actual string of the suffix, but rather they store just the starting index of that suffix. So that's a little nitpick that most of you get right. Then the next two are again correct about the construction. It was maybe tricky to say what is the naive construction of a suffix tree. what I meant by this is going by the definition. If it's a compact trie, the only way to construct them that I showed you was inserting starting with the standard trie and then compacting it. And already the size of the compact trie could be quadratic. So the naive construction, in the sense of building it from the standard trie, can be quadratic. But I at least told you that there's a linear time method, even though I didn't show you how it works. And finally, t has n leaves. That's not quite true. It has n plus 1 leaves. So that's not correct, but it's also not far from the truth. All right. So here that is again. I hope you're all still here. Maybe you can post a reassuring yes on the live chat, just to make sure I'm not talking only to myself. And I hope the live stream is working fine. In case there's any problems that the video lags or something, okay, great. Many yeses coming. Goody. So I hope you now all are up to things, how the suffix trees were defined and all these little nitpicks. So the next thing we were looking at last time was if we take a suffix tree and only look at how the leaves are arranged. Well, there was one thing that was important was to make sure that the children of a single node are arranged in alphabetic order of this first character, which is something we can always do. And if we do that, we notice that the strings represented by those leaves are in lexicographic order. They are sorted. And then the suffix array was exactly just storing only the order of the leaves in the order they appear in the suffix tree. And here if you draw this tree in the normal way, this would be left to right. This would be the suffix array. The suffix array would read the starting index in the leaves if you traverse the tree left to right. So we can forget about all of this tree and just store this array of leaves. And I showed you last time a little bit how we can search in this with binary search. Now again, just a little recap to make sure you're very up to date on this and also about the details of the definitions. Let me start again this question. Maybe this time actually give it a little longer. Okay, this worked fine this time. So I'll leave this page open because it's nicer to read until most of you have voted. So this again, this is basically just recap on the definitions that we've gone through last time and very briefly on the last slide. But it's important that you have those fresh in your mind before we move on. So this is the hard part. I'm sitting here and waiting, and I'm not sure how much time I should give you to answer those questions. In theory, there's just the roughly 10-second delay that the stream has, but then you also have to switch tabs, etc. Okay, you think you're done. I only see participants 6, which is not that great, but connected is 90. Maybe I'll give it a few more seconds. Unlike usually when I see you guys sitting in the class, it's very hard for me to say how many people are actually actively listening and participating in the questions. Maybe I'll have to do a different way to find a different feedback channel that allows me to see the crowd more clearly. There's 28 logged into the live chat. But then again, what does that mean? All right. More and more people post that they're done, so I think I'll stop it at this point. And well, lots of people have voted, so I guess I waited definitely long enough. Okay, let's briefly go through this. And so there's a clear point that B most people recognized, but we should maybe discuss E. But I want to go back to the screen where it's readable. Part A was correct. That's exactly the definition of the suffix array, and you recognize this. This, you noticed, is nonsense. It's not the path to the leaf that stores the number R, but it's the rth leaf in left to right order in T. So that's exactly what happens in the suffix tree. Then this and this is two different ways of writing the same thing. It's a notation I introduced at the beginning of the unit, saying T subscript I is the suffix that starts at position I. Sometimes convenient to have this more readable version of this, which is what it really means. So this is the rth smallest suffix in lexicographic order. That's also true, and it's an alternative definition of the suffix array. Then number E was a little tricky, because I definitely told you about suffix arrays as a space-efficient alternative to suffix trees, right? And this is very true, but if you look at the theta class, then indeed they're the same. Suffix trees take theta n space in words. They have a linear number of nodes, and each node is constant size, at least if we assume a constant alphabet. So this is like many things in this unit, we assume that the size of our alphabet is constant. If this is no longer true, things are not quite as clean, and it makes sense to assume that this is constant in many applications. So I'll stick with that. In that case, if the alphabet size is constant, each node in the suffix tree only needs a constant number of words, and then we're fine with this linear space. And on the other hand, the suffix array, of course, is also linear space. It stores a single integer for each entry, and there's n+1 entries. So that one was a little bit mean, because it is true that the constants are very different. So theta of n for both, but the suffix array stores the single number, and the suffix tree stores on the order of 10 numbers for each node, or something like this, depending on the alphabet size, depending on the details, if you need parent pointers, etc. pp. But that will definitely be the main motivation for suffix arrays. And the last point is what we've just discussed on the previous slide last time. We can use binary search to find matches of patterns in L. And apart from the text itself, that's all we need. But searching is a little slower. And to be precise, we had this logarithmic overhead coming from the binary search, which we didn't have, which you didn't need in the suffix tree. All right, so I'd like to move on then. I said motivation number 1 for the suffix array is the reduced space that we need. But there's also a second motivation, and that comes from the fact that it's much easier to construct also because the whole concept of a suffix array is much easier. It's a simpler data structure. It's just a single array instead of this complicated tree. And it's also possible to construct it with simpler methods. So let's see how far we can get with very elementary ideas. How can we compute this suffix array, the sorted list of leaves? One obvious thing, like we did it in the example, was we can construct the suffix tree and then do a left to right traversal to find all the leaves in order. But that's defeating the whole point. We wanted to get rid of the trees, so first building it and then throwing it away sounds very wasteful. But then at a second thought, we're asking a sorting problem, and we have sorting algorithms covered in this module earlier on. Why don't we just take one of those? And this is clearly the simplest you can do in terms of actually coding it. It has a downside. I mean, it's not the most stupid thing to do. It's okay-ish in some applications. So this is in the worst case it will be really bad, but there's reasons to believe, if you're not too unlucky, that this won't actually happen. But at least in theory, for the worst case, the problem is we can apply a sorting method to sort the suffixes, but whenever we compare two suffixes, we would have to take those strings and start comparing letter by letter. If those are all equal, we might have to read very long through these two suffixes before we find a mismatch and before we can decide which one is smaller. So it's in principle possible that every comparison takes theta n time, because it takes theta n time to go through the entire longest common prefix, and that would result in a linear slowdown of sorting, and sorting is the n log n. So that's how this comes. So it's trivial to code, but so slow that you actually could say, let's build the standard trie and do the suffix tree route. And we can do much, much better than this. And that will be the content of the rest of today's class. And by the end of this session, you should have at least an idea how you can construct suffix arrays in linear time, and very fast in practice too. The first thing I want to show you is a general method for sorting strings. So this is for the problem of sorting strings. It's fast not only for the case that we are sorting the suffixes of a text, it's in general a good idea. It's based on quicksort, and it has a slight twist to it. So this is a technique that might actually have belonged into the sorting chapter, but it's specific to strings. That's why I waited for it here, and it has a very nice application with constructions of suffix arrays. So it fits well in this chapter. The example is with a general list of words, just a set of strings, not suffixes of one text, just to illustrate this point. What the algorithm does is it tries to partition, like quicksort does, this set of strings by only looking at the first character for now. So initially we have this list of strings, and we pick one pivot string, she. And now we partition all those strings based on the first character only. So we take the first character of the pivot, which is S, and then we divide the strings into three groups: those that have a first letter that comes before S, those that have actually S itself as the first letter, and those that have a first letter that comes after S. That will be the partitioning, and it's called fat pivot partitioning because if you look at this middle segment, it looks, from quicksort's perspective, which only looks at the first character, it looks like a very, very big list of just duplicates of the pivot. In our case, there's not really duplicates because the words continue, but if you look at the first character only, it's all pivots, and so it's a fat partition of pivots. Now, a second important thing is, because these are all duplicates of the pivots, if you look at the first character, there's no need in the recursive calls to look at this first character again. We know all the words in this segment start with the same character. For the other two segments, though, we don't know this. It happens to be coincidentally that here both start with the T, and actually they're the same, but we don't know this at this stage. And as the first example here shows, it's not a general property. So Quicksort sorts all those boxes separately now. So if we go to the first one, we pick a pivot and we do the tripartition, those that start with the same letter, those before, there's actually none. And well, who can't sort? So this should of course be the other way around. And it will be wrong on the rest of the slides. But apart from that, I'll define my own alphabetic order where B comes before A. Very useful. The second recursive part, we pick the pivot here, he. Well, it's she, but we only look at the second letter. So that will divide this list into, again, 3 parts. The one where we have something that comes before H in the alphabet. It happens to be all E's, but again, that's coincidence. Then we have all the copies of H, which are already grayed out because we know they're the same, right? And then all the words that have as the second character something that comes after H in the alphabet. And we do the same thing for the last round, and here, of course, they're both in the middle partition, in the pivot partition, because they're the same. And we keep doing this until we have small, well, if we have a single element in a box, we don't need to do anything. A single element is sorted, except that your instructor redefined the alphabetic order. And here, in the next round, actually nothing happens. We see it's all E's, so this whole thing is the fat pivot partition again. It sounds like we didn't make any progress from here to there, but we did, because now the E is grayed out. So we never compare these first and second characters. That's something I said it before, but I might stress it again. In all what we're doing here, when we partition elements around this pivot element, well, I'm back in the first example, but you could do it the same way here. So if we partition elements around this pivot, we only look at the dth, say, character in these strings. We don't start comparing from the beginning again. That's how this method can be much more efficient than a standard sorting method that's blind to the fact that we're sorting strings here. All right, you can continue this example all the way down until you have well, boxes that contain only one thing, or you reach the end of the string, like in this case, and you actually found that these two strings are identical. There's a nitpick. If you reach the end of a word, but other words in this block do have more characters, then you pretend that those have, again, a dollar symbol that comes before any other. So that you would sort the two she's before the shells. And so on and so forth. That way you can recurse all the way down till you have single elements, like you would do in Quicksort. The only change to Quicksort really is how you do the partitioning. That's a pretty nifty method. If you want to see the details, this is described in the algorithms book that we've used before. There's also a video on that on qubits. The key fact, again, is we only look at a single character, and which one that is a parameter that we pass down the recursion. Initially, it's the first one, so we start with d equals 0. And then we create these 3 segments. On the first and third segment, we continue with the same d, but for the fat pivot partition, we continue with d plus 1. And by doing that, we make sure that we never compare these equal prefixes twice. That's the way how this method saves a lot of comparisons. And then in the book, again, it's shown precisely what the performance of this method is. I don't want to go into details on this, but if I was to implement a suffix array in practice, and well, if I had to recompute it from scratch, this would be the method I would try first, because there's good chances that it's actually fast enough for your application. Only for if you're using very big inputs and you're very tight on time, it makes sense to invest the time to implement the method I'll show you next. But let's look at this one more time. So it's simple to code, and it's efficient for many types of string sorting methods, and in particular for computing suffix arrays. So, and if you choose random pivots, you get n log n time, which is not too bad if you compare it with the n squared that we got from the simple standard trie construction. But we can do better in the special case of suffix arrays, and that's a major achievement in theory.